In this video, we'll cover some of the basics of lunar eclipses, phases of the moon, why the eclipse moon has a red color, and talk about some of the details of the upcoming January 20/21st, 2019 total lunar eclipse. So we first want to discuss why we have phases of the moon at all. So we have in this slide sunlight coming from up above. Of course, it comes from one spot and not all across space, but just illustrative sunlight coming from the top, coming towards the Earth-Moon system. The Earth and the Moon are not drawn to scale here. They're too big and too close to each other. But from our point of view on the Earth, we see the Moon apparently going around the Earth. That's not quite true. The Moon actually orbits the Sun. I'm not going to go into that in this video, but the Earth's gravity pull distorts the orbit of the Moon. And from our point of view, we can talk about the Moon going around the Earth. The important phase is full moon for the discussion of a lunar eclipse. At full moon, the Sun is on one side of the Earth, the Moon is on the other side, and consequently the half of the Moon that we see is fully illuminated compared to other phases where the half of the Moon that we see can be partially illuminated for the quarter phase or crescent phase and so forth. But at full moon, the Earth is in between the Sun and the Moon. And most months, full moon is uneventful, but if there's a certain special alignment of the Sun, Earth, and Moon, then we can get a total lunar eclipse for an hour or so. So first, to talk about the Earth and Moon to scale. In this slide, we have the Earth on the left here, and hopefully you can see this little dot on the right that represents the Moon. If you would like to set this up for yourself, hopefully you could find a basketball, let that be the Earth, and place it on the floor, and then find a tennis ball and put that tennis ball 24 feet away from your basketball, and that would be the scale of the Earth-Moon system. And you will take note that there is a good deal of separation here. The International Space Station and the Hubble telescope, those orbit close to the Earth. The Moon does not orbit close to the Earth. And as a consequence, it's often the Moon is not in the shadow of the Earth. If you'd think of the Sun off to the left here, this would be the phase of full moon with the Sun off to the left. The Earth's shadow is coming back here, but the Moon doesn't always pass through that shadow at the phase of full moon. We'll get to that in just a minute. So to get a total lunar eclipse, we need to have the Moon moving into the shadow of the Earth, and therefore, to get the Moon in the shadow of the Earth, the Sun has to be on the opposite side of the Earth from the Moon. And in this drawing, again, it's not drawn to scale, but let's start with the Sun and the Earth. And here's the path of the Earth around the Sun, the Earth's orbit. From the point of view of someone on the Earth, looking at the Sun amongst the stars on the sky, the Sun's path across the sky is called the ecliptic. In this drawing, we're seeing the Earth's orbit. The Moon's orbit is not in the same plane as the Earth's orbit around the Sun. If you would, again, take a couple objects, not to scale, but let's say a tennis ball representing the Sun and a marble representing the Earth, put those on a table and then move the marble for the Earth around the Sun, that tabletop would be the plane of the Earth's orbit. Then we have the Moon. The Moon could not properly be represented by another marble rolling on the table around the Earth. The Moon's orbit is tilted, it's inclined at about 5 degrees compared to the tabletop, compared to the Earth's orbital plane. And that has a big consequence for lunar eclipses. To get a lunar eclipse, we need pretty good alignment between the sun, Earth, and moon. So where my arrow pointer, my cursor, mouse cursor is pointed here, we would need the moon more directly in line. This drawing is nice in that it represents what happens for most months at full moon. The moon is above the Earth's orbital plane, or for a certain number of months, half the months of the year, the moon at full moon is below the Earth's orbital plane, and it's below far enough that it misses the Earth's shadow. The moon does not move through the Earth's shadow during this phase of full moon. So we need this special alignment, and I'm not going to go into it, but that's what's labeled node on the drawing here. When the moon is in the tabletop, on the tabletop of the Earth's orbital plane, then we would get an eclipse. And I'm not going to talk about solar eclipses here, but this discussion also applies to that. So here's another attempt at describing what's required to get a total lunar eclipse. We need the moon on the ecliptic on the sky. That's the path we see for the sun through the stars, called the ecliptic. And we need the moon on that location on the sky to get a total lunar eclipse. In terms of alignment, we need sun, earth, and moon in pretty much a straight line. Here we have the case of no eclipse for a full moon. Sun, earth, and the Earth's shadow is going to be underneath my moon here. That's represented in this text illustration. The moon at full moon is not going to pass through the Earth's shadow because, again, the moon's orbit is inclined at this 5-degree angle, and here at full moon, the moon in space is passing above the Earth's shadow, so no eclipse occurs. What about the color of the moon during a total lunar eclipse? Well, I'd remind you that there is a definite color to the sky, to the sun, although don't stare at the sun, never point binoculars or a telescope at the sun, but I think you'll agree the sunsets are red, sunrises are red. The reason for that is that red light is better able to pass through our atmosphere than blue light. I won't go into a discussion of why the sky is blue, but it relates to this as well. But at sunset, the red light is surviving. It's getting to us, not being scattered by the Earth's atmosphere as the blue light does. So we don't have blue sunsets, we have red sunsets. The red light is able to pass through the Earth's atmosphere and reach us. Same thing happens during a total lunar eclipse. The Earth's atmosphere, red light passes, some red light passes through the Earth's atmosphere and is scattered into the Earth's shadow. The Earth's shadow is not perfectly dark. There is light inside that shadow, and the Earth's atmosphere is supplying that light. And depending on how much volcanic ash or dust is in the Earth's atmosphere, there can be a different quantity of this red light inside the Earth's shadow. So different eclipses will have different colors of the eclipsed moon, but basically all red, just brighter or dimmer. And that makes them interesting for people to view over and over and over. I've seen several total lunar eclipses, but they're always nice to see, to pick out how red that eclipse moon is going to be. So let's talk about this particular eclipse. So here in this red circle, this would be the shadow of the Earth, the shadow of the Earth. And we are getting a total lunar eclipse because our full moon is passing into the Earth's shadow. If the full moon was down below the Earth's umbra, we would not get a total lunar eclipse. And if the moon just kind of grazed across the Earth's umbra in its motion, it would not be a total lunar eclipse, it would be a partial lunar eclipse. So umbra is important. So if we have these eclipse contact times, U1, that's an important time. That's when the moon is just first contacting the umbra of the Earth. So we're going to get the start of the partial eclipse. and we'll have partial eclipse until U2, the time of U2, when the moon is fully inside the Earth's shadow. And then at U3, the moon is starting to leave the Earth's shadow, and at U4, the end of the partial phase on exit, at U4, the moon is totally outside of the Earth's shadow. The times over here are universal time, the time at Greenwich, England. And I want to go into what happens for Central Time on this next slide. In the United States, this eclipse is going to be on Sunday night, January 20th. And the universal time can be dealt with, converted into Central Standard Time, or the time zone where I live. If you subtract 6 hours, you'll get the Central Standard Time. So universal time, it's January 21st for someone in England, but for the United States, it's January 20th when this event starts. And subtracting 6 hours from that U1 time on the previous slide means that the moon is going to start entering the Earth's dark shadow at 9:33 p.m. Central Time. This would be 10:33 Eastern Time. It would be 8:33 Mountain Time. It would be 7:33 Pacific Time, where some friends of mine in Oregon may be viewing this eclipse. At 10:41 p.m., then we get the start of the total eclipse. This is the main event. Between these two times, as you observe the sky, you'll see the area on the moon that's dark get larger and larger. And also, hopefully take note that this area has a curved outline to it. It's not a straight line of darkness moving across the moon, but the Earth is a sphere. The Earth's shadow has a curve to it. So you should see a definite little curvature going across the moon. 10:41, we get the start of the total eclipse. 11:12 p.m. Central Time, the moon is most fully inside the Earth's umbra, the Earth's dark shadow, and that's when we'll have the dimmest total lunar eclipse moon. 11:43, the total eclipse is finished, and we have partial eclipse now until 12:50 a.m. on the 21st, and the moon is exited the Earth's umbra. So there we have our timings converted into Central Standard Time. Let's talk about where we can see this eclipse. This is a good eclipse for the United States in terms of relatively convenient time, late evening. In the United Kingdom, this is going to be like a 4 a.m., 5 a.m. event. So not quite so convenient, but they'll still be able to see the full sequence of actions here as the moon moves through the Earth's shadow. But the United States will be, the moon will be nice high in the southern sky, and relatively convenient times we'll be able to see all portions of the eclipse at a convenient time, convenient place in the sky. Individuals in India, individuals in China cannot see this eclipse at all. The situation here is that this is the last total lunar eclipse, I believe, conveniently visible in the United States until 2021. I did not look that up recently, but that's my memory. So take advantage of this, January 20th, 2019, and you'll see a total lunar eclipse with convenient viewing times, convenient position in the sky, and this won't come around again until 2021. So with that information, I hope you understand a little better now why eclipses occur, lunar eclipses occur, why the red color occurs as red light filters through the Earth's atmosphere and is able to reach the lunar surface. And hope your sky is clear. If you'd like some more information on astronomy, I have an annotated list of my videos, YouTube videos, astronomy.gpclements.com. And also at this site, there's a 2-page list of events for the sky for 2019. This is mostly focused for people in the United States viewing the sky, but there's things that are applicable around the world. But astronomy.gpclements.com, there are short lectures and example problems worked out, and discussions of astronomy topics, Hubble pictures, and so forth. If you're interested in physics, short lectures and worked out problems for an introductory physics course, physics.gpclements.com would be your link there. And then hopefully if you find some of this information useful, go ahead and subscribe to my YouTube channel. I hope you enjoy the total lunar eclipse of 2019.